AB Calculus, Section 4.7, L'Hopital's Rule. L'Hopital's rule is the definitive way to simplify evaluation of limits. It is not directly evaluating limits, but only simplifies evaluation if used in an appropriate setting. In effect, this rule is the ultimate version of the cancellation tricks that we've talked about. The others were factor cancel, conjugate cancel, as well as clear fraction, right? So those were labor intensive. Right, we're going to use L'Hopital's rule to keep it much simpler. Applicable in situations where a more down-to-earth, genuine algebraic cancellation may be hidden or invisible to some sense. Suppose we want to evaluate this limit, where the limit a could be infinity or negative infinity in addition to ordinary numbers. So suppose that either the limit of the numerator and the denominator equals 0, or the limit of the numerator and denominator are uncountable, as you can see in this situation. All right, either 0 taking the form of 0 over 0. Right? Of course, we never want to put equivalence attached to that. Right? But if it fits this form, or it fits the form plus or minus infinity over plus or minus infinity, those are the two indeterminate forms which apply to L'Hopital's rule. All right, now as we look further down here, you can see that the plus or minus doesn't have to be the same sign on top or bottom. We can just plug in to evaluate the limit, and these are traditionally called indeterminate forms. The unexpected trick, though, that works, actually amazingly, is that we are able to take the derivative of both the numerator and the denominator and re-evaluate. So the process of L'Hopital's rule is going from one limit here to the next. We take the derivative of the numerator and the derivative of the denominator, and then we simplify. So our first step is to take the derivative separately. Okay, and please, no quotient rule. No quotient rule. Okay, and then we simplify. And then we evaluate again. Now, it is possible that you could have to use L'Hopital's rule more than once. We'll see maybe an example here pretty soon. Reiterating, this is not the quotient rule. It is not so clear why this would help either, but we'll see in the examples to follow. So let's get into it in an example. All right, let's take a look at example 1 here. If I were to take a traditional approach to this question, I would simply insert a 0 in for x in both numerator and denominator. Notice in this case we would get sine of 0, which is 0 over 0, which of course is an indeterminate form of which L'Hopital's rule applies. So what we would say is, since the limit as x approaches 0 of sine x equals 0, and the limit as x approaches 0 of x equals 0. So here I've got the limit as x approaches 0 of the numerator, the limit as x approaches 0 of the denominator, both equal to 0. Then, by L'Hopital's rule, the following is true. The limit as x approaches 0 of sine x over x would be equal to the limit as x approaches 0 of each of the derivatives. The derivative of sine x is cosine x. The derivative of x is 1. The limit as x approaches 0 of cosine of x over 1. Now I simplify. Of course, I take the derivatives, right? That's our first step, derivatives. Then the second step is to simplify. Well, there's not a whole lot of simplifying I can do here. When I simplify this expression, it just is the limit as x approaches 0 of cosine. And then I re-evaluate. Okay, when I evaluate this limit, the limit as x approaches 0 of cosine of x is cosine of 0, which happens to be 1. Okay, therefore, by L'Hopital's rule, the limit as x approaches 0 of sine of x over x is equal to 1. And we already knew that. That was one of our special limits. But here is an application of L'Hopital's rule in finding that limit. I think prior to this, we had used the squeeze theorem. It's a different method to get us to the same result. Right? But L'Hopital makes this much simpler. All right, let's look at example 2. Find a limit as x approaches 0 of x over e to the 2x minus 1. Okay, so if we were to do an evaluation immediately using direct substitution, you'd see that you get a form of 0 over 0. That's an indeterminate form. Specifically, an indeterminate form, as we mentioned, which is aligned with L'Hopital's rule. So we state, since the limit as x approaches 0 of the numerator is equal to 0, and the limit as x approaches 0 of the denominator is also equal to 0, then by L'Hopital's rule, and yes, you do need to write this out each time, then by L'Hopital's rule, the limit as x approaches 0 of x over e to the 2x minus 1 is going to be equivalent to the limit as x approaches 0 of each of those derivatives individually. So the derivative of x is 1, the derivative of e to the 2x minus 1 is 2 e to the 2x. Now let's evaluate, because there's not a whole lot of simplifying we can do there. Actually, there's none. The limit as x approaches 0 of 1 over 2e to the 2x is going to equal 1 over 2 times 1, which is 2. Therefore, by L'Hopital's rule, the limit as x approaches 0 of the original, x over e to the 2x minus 1, is equal to 1/2. All right, let's look at a third example. Looks like that squeeze theorem is just going to come tagging along with us. Okay, let's look at, again, a direct substitution. If I plug in infinity, so to speak, in the numerator, I'll get a really large number. And into the denominator, I'll also get a really large number. Now, I don't care how large they are, I just know both will end up heading toward an uncountable value, a positive uncountable value as well. Therefore, since the limit as x approaches infinity of x squared trends to, don't write equal, trends to infinity, and the limit as x approaches infinity of e to the 2x also heads toward infinity, then by L'Hopital's rule, then we know that the limit as x approaches infinity of x squared over e to the 2x will be equal to the limit as x approaches infinity of their derivatives, which is 2x over 2e to the 2x. Now we reevaluate. Not anything I can do there with, I suppose I could simplify just slightly. Reducing the 2's, that would be the same as the limit as x approaches infinity of x over e to the 2x. Now notice that this also will take on an indeterminate form, infinity over infinity. Therefore, I'm going to use L'Hopital's rule again. Since the limit as x approaches infinity of x trends to infinity, and the limit as x approaches infinity of e to the 2x, excuse me, heads to infinity, then by L'Hopital's rule, I'm going to abbreviate here because I'm running out of space. Don't abbreviate on the AP exam, please. Then the limit as x approaches infinity of x over e to the 2x is going to be equal to the derivatives evaluated at infinity. So that'll be 1 over 2e to the 2x. It's going to come out to be the exact same, right, as we can see in the problem before. Therefore, since the limit as x approaches infinity, my writing's getting a little sloppy here, I'm sorry about that, of 1 over 2e to the 2x is equal to 1/2, then the original limit here as x approaches infinity of x squared over e to the 2x will also equal 1/2 by L'Hopital's rule. Now all these steps are necessary, you guys. We cannot set equivalence to infinity over infinity. We have to state that since the limit of the numerator heads to infinity and the limit of the denominator heads to infinity, then by L'Hopital's rule, here's our statement. We reevaluate, we get another indeterminate form. We start back at the beginning. Since the numerator goes to infinity as x goes to infinity, and the denominator goes to infinity as x goes to infinity, then by L'Hopital's rule, we've got another equivalence statement. We evaluate that limit yet again after we simplify, and it looks like we get 1/2. Then we can tell that the original limit would also go to 1/2 as x approaches infinity. Let's look at one more slide here. All right, example number 4. Limit as x approaches infinity of natural log of x over x minus 1. This will also take on an indeterminate form. Natural log will go to infinity as x increases without bound. So will the linear function x minus 1. Okay, so I go through my normal steps. Since the limit as x approaches infinity of ln of x heads to infinity, and the limit as x approaches infinity of x minus 1 trends to infinity as well, then by L'Hopital's rule, do as I say, not as I do. I had to abbreviate for spacing. Then the limit as x approaches infinity of ln of x over x minus 1 will be equivalent to the limit as x approaches infinity of 1 over x over 1. Now, the limit as x approaches infinity of 1 over x is equal to 0. Therefore, using L'Hopital's rule, we now know that the limit as x approaches infinity of the natural log of x over x minus 1 is also equal to 0. All right, let's take a look at example number 5. This comes from an AP example in 2016. And this limit is interesting. As you can see here, if I were to evaluate plugging in a pi, the cosine at pi is -1. Sine at 2 pi is 0 plus 1. So I get -1 plus 0 plus 1. That'd be 0 on the top. And if I insert a pi, I get pi squared minus pi squared, which is also 0. So I'm getting an indeterminate form of 0 over 0. All right, now, if it were me in a multiple choice question, I wouldn't write down all the formalities, right? I would just go straight to it. So I'm going to model this as if I'm taking the AP exam, not as if I'm taking an exam in our class. I would just go straight to L'Hopital's rule, because they will not grade. work on the multiple choice portion of the exam. We will, though, so you do need to go through the steps above, saying that since the limit of the numerator equals 0 and the limit of the denominator, all that good stuff. Okay, so using L'Hopital's rule, I know that I can now just evaluate the limit as x approaches pi of the derivative of the numerator, which would be negative sine x, that's the derivative of cosine x, plus 2 cosine 2x, and then the 1 drops off. In the denominator, I would take the derivative of x squared, which is 2x, and the derivative of pi squared, which is 0. Now the limit of this would be equivalent to negative sine of pi plus 2 cosine of 2 pi all over 2 times pi. All right, negative sine of pi is 0. 2 cosine of 2 pi is 2. So 2 over 2 pi is 1 over pi. Therefore, I know the original limit is 1 over pi. Now, I've modeled work that I would only do on the AP exam on a multiple choice question, not a free response question. Okay, let's look at example 6. Very similar here. If you were to insert a 3, you would get tangent of 0, which is 0, over 3 times e to the 0, which is 3, minus 3, which is also 0. So yet again, I'm going to model multiple choice AP exam work. Therefore, by L'Hopital, and I probably wouldn't even write down L'Hopital's here. That'd be a waste of time. But I would take the limit as x approaches 3 of the derivative of tangent of x minus 3, which is secant squared x minus 3, over, this will end up being 3e to the x minus 3 minus 1. Okay, so the secant of 0 is the reciprocal of the cosine of 0. Cosine of 0 is 1. So this would be the same as 1 squared. If I plug a 3 in the denominator, I would get 3e to the 0, which is 3. Okay, 3 times 1 minus 2, which would be 2. So I get 1 squared over 2. And therefore, I end up getting an answer of 1/2. Therefore, that limit evaluates to 1/2. All right, guys, that's it on L'Hopital's rule. Hope you guys have a great day. We'll see you in the next video.